Okay, one of the things I wanted to show you is an induction proof. This is actually an important part of proofwriting classes, and somehow, again, because we don't have that foundations of logic class in our program, you can actually slip through and not have done an induction proof yourself. So I wanted to give you one example, and as we are building up our techniques, I'm going to hand out a proofwriting guide, and one of the things that you can choose in selecting to a strategy is an induction. So I'm going to prove something that came out of a number theory book, that the sum of cubes, the first n cubes, turns out to be the same thing as the sum of the first n quantity squared, which is kind of bizarre actually, because when you square something out, you FOIL it, you have this inner term with a 2 in it. It seems kind of strange that you're supposed to get this sum of cubes at the end. So I never believe anything when I look at a statement like, is that true? That's exactly how I look at the entire world. Is that true? Is what they're telling me true? And I question it. So question it. That's the process. You look at it and say, this is a bizarre formula. I question it because it seems like it shouldn't be true. It seems like when you square something out, you're going to have a lot of inner terms, right? FOIL. And it doesn't seem like everything will disappear and you get a bunch of cubes. So if I try out just like n equals 1, well, 1 cubed is 1 squared, so it really doesn't tell me anything. But yeah, it works. I can tell you that it works. But what if I try the first two? 1 cubed plus 2 cubed. Is that the same thing as 1 plus 2 cubed? Well, I can actually run the numbers and see I get 3 squared on the left side, and I get 8 plus 1 on the other side, and it works. But I want to do more than that. I want to use the numbers to figure out why it's working, because, again, I actually am named for the Doubting Thomas. If anybody here is Catholic, St. Thomas came to India right after Jesus died and tried to convert people, and I'm named for him. I'm one of the original Syrian Catholics down that dynasty, so I doubt everything. I don't believe it. So I'm still doubting it and saying, why does this work? Why did it show up this way? And I get this 1 plus 8 on the left side, and I have this 2, and I'm expanding the numbers, and I still see 9 equals 9, but I don't see the mechanism of why that should be true from the numbers. And I like to work with the numbers rather than symbolically, because numbers have a feel to it. You can actually get your hands dirty and see something. So my thing was, I still don't believe it. I'm going to go a little higher up and see if I can figure out why this is working, and maybe somewhere it's going to flake and it's not going to work anymore. So my next question is, if I went to 3 of them, will it still work? Well, what I notice now is this part I already know the answer to. I know that that part equals 1 plus 2. I just did it. So I know that these two are the same. So if I did that, is there a way that I can take the information from the previous run through and see why the next one is working? Well, I have a 1 plus 2 on this side also. I can group them together and then use FOIL to square that out. And I'm playing with the numbers. Of course I can add, trust me, maybe I can. I'm actually terrible at arithmetic. But you can add this up on a calculator and show that the left side's the same as the right side. I want to see why it's working, because it seems to me counterintuitive. And the reason it seems counterintuitive is because of these kind of things that you get when you square out stuff. But if I know that this part is 1 plus 2 squared, and I have a 1 plus 2 squared on that side, and they already match, what that means is the leftover part has to be the last number cubed, right? Just by algebra applied to numbers. So I have to figure out really, why did it end up that 3 cubed was the leftover part? So I took that piece, that red piece over there, and I started playing around with it. And what I noticed is, if I did some factoring, so I have a 3 here and a 3 here, if I factored out the 3, what I got inside was the sum of the first 2 numbers. And you probably don't remember this, but this is Gauss's formula. If I add up the sum of the first n numbers, you get n times n plus 1 divided by 2. You might wonder why would someone remember that? Well, I see it. Every time I teach Calc 2, I see it. Second, my son has this wonderful exercise. 15 push-ups, followed by 15 crunches. 14 push-ups, followed by 14 crunches. His cross-country coach showed him this thing. And so he said, you're actually doing quite a bit of push-ups and sit-ups as you're doing this exercise. I said, actually, yeah, you are. You're doing the sum of the first 15 numbers, which turns out to be 15 times 14 divided by 2. So since I work out every day, I remember that now. See, math and exercise go together. Get in shape and get smart. Those 2's cancel. So that's the Gauss's formula I was telling you about, which is also, you can use induction to prove that too. And where did you see this? You saw this, the sum of arithmetic series in Calc 2, at the end of Calc 2. All right, so I kind of am getting an idea of why this is working. And I'm getting an idea of how to put it together. And I'm just going to test it out with one more. So it's a lot of free play with math. I'm just goofing off with the numbers and seeing why it works. So that guy is Gauss. I'm going to group together first. And if I group it together, I get that. I've already done it for 3, so I kind of have a feel for what's going on with 4. From the last slide, I already know that answer, right? I already know that the 1 plus 2 plus 3 quantity squared is 1 cubed plus 2 cubed plus 3, because I just did it on the previous slide. And I have this leftover part, but I already played around with this. I know that if I do the factoring of the 4, I get 1 plus 2 plus 3, and I can apply Gauss's formula right there. So everything drops out, and it turns out that I get exactly 1 plus 2 plus 3, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. So I'm seeing why it works now. And now I'm ready to actually prove it in general. I could do it again. I could go to the 5th one and take the information on this slide and use it to play around with the 5th one to show that it works without actually adding everything. And then I could use that information for the 5th one and do it for the 6th one, and so forth. But that's going to get, we're going to run out of time. Can't do that. That's not today's lecture, where we just keep doing that again and again. So assume that I just kept going and everything was fine. And I kept going and I'm at the kth one. So I know it worked for the kth step. I just kept going. I just did the 5th one, the 6th one, ... I got the kth one. It worked out right. Can I symbolically get to the k plus first one? Because that tells me that that maneuver from the previous to the next one's working. That assumption of the kth one working is called the induction hypothesis. So you might have seen this already in a different class, and if you saw it the way I saw it, I remembered it as a process. Prove it true for n equals 1, assume it true for n equals k, show it true for n equals k plus 1. Now from this, you should get why that whole process is there. This is the reason. It's like you just got tired and said, I'm going to just pretend it worked for the kth one, and then use that to go to the next step. So can I get from that thing to the next thing? Just like I did with the numbers. Well, I know what to do. And important in all of this is that I believe it, because I worked the numbers. So it's not, for me, it's not enough to do n equals 1. I need to do enough before I believe it. And it's really, really hard to convince me. So I had to go all the way up to 5 to believe it. So here I am, I believe it. And I even have an idea of how it all gets put together because I played with the numbers enough. So I have this junk on the right side. I'm going to expand that, and I'm going to expand it the same way I did with the numbers. I'm going to block together the first group of people, right there, and then I'm going to FOIL out the rest. But I know from the induction hypothesis that this part, that's just from the top, right? I can just pull that top part down. So the black becomes the black. And here, I'm going to use Gauss's formula. The sum of the first k integers is k times k plus 1. Just the same thing I did with numbers, but now there's a letter in the place. And the last one is k plus 1 squared. So again, that came from an induction hypothesis. That part came from Gauss's formula. And the 2's cancel just like they did with the numbers. And I get this little bizarre thing at the end, the k times, well, I'm going to factor out factoring by grouping, which students at pre-calc level hate, but it's really important, right? Factoring by grouping is really super important. So take out a k plus 1 to the, I think I took it out to the right, and I get exactly the formula I want. So I was able to assume everything was fine up to the k step and use the k step to get to the k plus 1. So that means I don't have to do one after the other and keep going. I arbitrarily showed it that it always works, that the machine works. Yep, worked. That's called an induction proof. And so then you say the formula works, because I can get to the next step from the previous, so it works in general, because I didn't specify what k was. So when do you use induction? It's when you have to show something with an n in it, and it looks really long and messy, and it has an arbitrary n in the formula. And that's a typical flag that induction may be the appropriate hammer to apply. So here's the homework for this week. We are now in the section of factoring by primes. So somebody used on their in-class assignment. That's called the fundamental theorem of arithmetic. You don't want to go ahead in anything in the book and use something, because some of the previous stuff is used to prove it's a circular argument. So you'll use some of the previous theorems to prove the fundamental theorem of arithmetic.
So we're in section 2 now?
Yeah. And number 1, I just gave you an extra proof of divisibility. One more.
That's a 6, right?
Yeah, it's divisible by 6. You already have them done?
Oh, me?
Yeah.
Oh, no, I was pointing at my hat to my Rangers fan behind me.
Oh, I thought maybe you had all the answers on the back of your hat.
Oh, I wish.
I did it all last night, and I put it all on my
I'm
hat.
sitting here like this right now.
Of course, you need a magnifying glass. Everybody got it down?